We're going to look at some homework that we had on page 215 last night, 1 to 6. We want to look at 3 of those questions, 1, 2, and 3. First one says, why is G, big G, that's the one that has a value of 6.67 times 10 to the minus 11. Why is that called the universal constant? Anybody have an answer for that? Yeah, Demi? Yeah, exactly. It's exactly what I would say, because it can be used anywhere. And when we use the equation that describes Newton's law of universal gravitation, Gm1 m2 over r squared, this equation describes the force of gravity between any two objects in the universe, anywhere in the universe. Okay, it's a universal constant because it describes the force of gravity between you and Mackenzie next to you on Earth, but it also describes the force of gravity between some star in a distant galaxy and some other star in some other galaxy. Okay, that constant is the same no matter where we are in this entire universe. That means it is a universal constant. Number 2, describe how a torsion balance can be used to determine the gravitational constant. We looked at this on Monday, last thing we did on Monday, right? Remember that Cavendish torsion balance experiment? Someone said something about potatoes. Okay, and we joked about that, and it's like, well, Cavendish PEI. Not quite, but same name. You have this fixed top, this fixed ceiling, and then you have this thin wire hanging from this fixed ceiling, and on the end of that thin wire you have a rod, and on the end of that rod you have a mass that we call M1. Now there's a mass on the other end of it as well. It doesn't really matter so much about that mass, but we got to keep it balanced, right? So got something there. We're going to bring another mass that we're going to call M2 nearby. So we bring it nearby like this, and then it's going to cause a force of attraction. It's going to pull M1 towards it. We can measure the value of M1 easily. We can measure the value of M2 easily. We can measure the value of R, R being the distance that separates them center to center, right? Somebody was asking me at the beginning of class here, just before class started, about one of the questions from your unit assignment, and I can't remember which question it was, and I can't even right now for the life remember who it was that asked me the question. But the question was essentially this. We had, I think it was a planet or something, and then we had a satellite or something a certain distance above the planet. Did we need to add the distance from the surface of the Earth to the planet, or from the surface of the planet to the satellite to the radius of the planet? The answer is yes. Okay, we're using force of gravity equation. We need to use the distance from the center to the center. And if one of the objects is a planet, the surface to the center is the radius, and we need to include that. We can measure R fairly easily here, using a ruler or whatever. F is the trickier one. F we can determine, but not as easily as we can determine the other ones. Where does F come from? Where does F come from? Yep.
Force of gravity.
No. Well, it is the force of gravity, right? But we can't calculate it that way. Yeah.
The torsion of the wire.
Yeah, it's the twisting of the wire. Good. The amount of torsional properties or the twisting properties of the wire. The more it twists, the more the force is. The less it twists, the less the force is. So we can get an idea as to how much force was applied by how much the string or the wire twists when that force of gravity attracts M1 to M2. Now we've got F, R, M1, M2. The equation that relates all these together is Newton's law of universal gravitation, G M1 M2 over R squared. And we just, for Cavendish, just rearrange this to solve for G. F times R squared over M1 times M2. Cavendish does this little experiment, and he comes up with a value for G of about 6.67 times 10 to the minus 11. Now, of course, if you're Cavendish doing this for real, you're probably going to do this multiple times, maybe involve some graphing and so on. But in essence, this is what it is. This is what we need to do to find the value of G. Finally, question number 3 says, suppose Fg is the magnitude of the gravitational force between two people with this separation distance. How would Fg change if the separation distance became 2 meters and if one person was joined by an equally massive friend while at this 2 meter separation distance? if this is my force of gravity, it is, right? How would that force change if I made the distance twice as much? It would get smaller. By how much? Not twice. Factor of 4. How come? Because it's squared. So really what we'd be doing, we could say this is my original force. This is more of a physics 30 thing as well, but it's a really good thing to introduce here now. This is what my force was, my original. This is what my force is, my new force. My new force is Gm1, m2 over, what do we make it, twice? Yeah, 2. So it's over 2r. Well, r was the distance to separate it. Now the distance is 2r. It's twice that, right? Which if I square that and bring it out, it becomes so we just say the new force is a quarter of what the force was. Okay, it becomes a quarter of what we expect because it was squared there. The second question, one person was joined by an equally massive friend while at this 2-meter separation distance. So let's make one of the masses 2m here. This becomes 2 Gm1 m2 over 2 squared is 4 r squared. So what's the force become now? 2 over 4, or 1/2 of what it was. So if you just double the distance that separates them, then it's going to become 1/4 of what it was. If you double the distance and double one of the masses, then it's going to become 1/2 of whatever the force was before. I want to move forward now and talk about a new concept with gravity that helps us to describe a certain situation when we don't have a force. I got a board marker in my hand right now. It experiences a force of gravity because of the Earth. Agree? Yeah, there's mass of the Earth, there's mass of the board marker, and because of those two masses, there's a force of gravity that pulls the board marker toward the Earth. If I drop the board marker, look, it falls because it's attracted toward the Earth. Curvature of space-time and whatnot. What happens, though, if I put the board marker away? Like I look at that spot where the board marker was sitting in my hand. It's not there anymore. It did experience a force of gravity when it was there. Now it doesn't because it's not there. But remember what causes gravity. Remember that day we spent so long talking about space-time and the dent in the fabric of space-time? That's still there. The Earth still dents the fabric of space-time and causes what? If there's nothing there to experience a push or a pull, there's no force of gravity. We have to have a way of describing gravity when there's nothing to be pushed or pulled. In other words, we have to have a way of describing gravity when there is no force. Just because that board marker is there, then I take it away, that doesn't mean that gravity has disappeared. But the force of gravity has disappeared. The way we're going to describe gravity in the presence or absence of the board marker experiencing gravity is by talking about gravitational fields. We're going to say a gravitational field is a region in which a gravitational force can be experienced. I'm going to underline that. Doesn't mean that it is being experienced. It can be experienced by an object. So what's the gravitational field surrounding the Earth? Well, it's the region around the Earth where if I put a board marker there, there's a force. If I put a board marker there. If I don't put a board marker there, the force is not there, but the field is. Because you would experience a gravitational force if the board marker was there. So we're describing this mysterious, invisible, gravitational thing, curvature of space-time, when there's nothing there to experience it. Like the board marker isn't there to fall. We're just saying, if there was something there to fall, guess what would happen to it? It would fall. Yeah, question?
When you describe this, are you describing like...
Gravitational field shows us the influence of a mass that produces gravity. Right? The things that produce gravity dent the fabric of space-time. This describes for us in a nice, neat, tidy way the influence of something that produces gravity when there's nothing there to actually experience it. Remember, to have a field, all you got to have is a producer. Field caused by the Earth, all you got to have is the Earth. To have a force, you need the field caused by the Earth and then something there to experience it as well, something to feel the field. Gravitational fields are what we call vector fields, and you can imagine why we call it a vector field. There is a direction associated with it. Now, if I put the board marker in the gravitational field, it's influenced, not just influenced, it's influenced in a particular direction. I don't drop the board marker here and watch it go in a random direction. It will go down. It will be influenced downward every time. There is a direction associated with the influence. It's downward, toward the producer. So it's a vector field. If it was a scalar field, then it would just, I drop it and it would just go in a random direction. It would be influenced by the Earth, but not in a particular direction. All masses will experience a force or move in the direction of that field. So like, we know that this board marker would move downward if I let it go. But so would this box of Kleenex, so would a calculator, so would you. If we dropped you in a gravitational field, every object of mass will experience a force in the direction of the field. So picture this. Okay, here's the Earth. There is nothing around the Earth. Nothing. No board markers, nothing around the Earth. There is a gravitational field that surrounds that Earth, and it points this way. And that's there no matter what. As long as the Earth is there, that's there. We're not saying that there's something falling in the direction of those green lines. We're saying that there's something that would fall if there was something there. So all of a sudden I put a board marker or a rock right here. What happens to it? It falls downward. The red is the force, right? Green is there no matter what. The red force is only there if there's a producer, like the Earth, and the board marker or a rock to experience that field. Does that make sense? Producer, a field, all you need is a producer. To have a force, you need something to cause it, the producer, and you need something to experience it. That would be the board marker or the rock. Now, if I put a board marker right here, which way would it go? Up toward the Earth? No, don't say northwest, because we're not talking about northwest, southeast frame of reference here. Which way would it go? Up toward the Earth? Yeah. No, it would go down toward the Earth. See what I mean by that?
Perspective.
See what I mean by that, though? Gravitational field lines point down. Okay, no matter where we are on or around the surface of the Earth, the center of the Earth is down from us. So if the field line is pointing down toward the center of the Earth, the object will experience a force, if there's one there, down toward the Earth. We get a couple equations to describe gravitational fields. Remember, there's that force equation. This isn't new. I'll put this above here because it's one that we've dealt with for a couple days now. That's my gravitational force. And remember, as long as you have something that causes the field and something that experiences the field, then you'll have a force. But you need two things, right? You need an M1 and you need an M2. You need an Earth and you need a board marker. You need a sun and you need a spaceship. You need two things to have a force of gravity. In order to have a field, all you need is one thing, and that's the producer, what causes it. Gravitational field is given by the symbol G, little g. It's a vector field, so we put a little arrow over it. But we're also going to put these absolute value signs around it, meaning that although there's a direction, the equation is not going to tell me what the direction is. It's just going to give me the magnitude. Little g is equal to big G times m over r squared. It's almost the same as force, right? What's it missing? It's missing a mass. This is the gravitational field strength. G, of course, is 6.67 times 10 to the minus 11. This is the distance from the center of the producer in meters to wherever it is that you're trying to find the field strength. If I want to find the field strength 20 meters above the surface of the Earth, then I need the distance from 20 meters above the surface to the center of the Earth. So I would add that 20 meters to the radius of the Earth to get that distance. M stands for the mass of the producer in kilograms. Okay, we keep talking about the Earth and the board marker on purpose. Keep talking about the same two things on purpose. Which one would be the producer here, the board marker or the Earth? The Earth. So we would use the mass of the Earth if that was our question. What do you think we call this equation? Take a look at what you see up here, trying to come up with a good name for this equation. Yeah, that works, gravitational field strength, although there is another one, so we have to be able to distinguish between this one and the other one. I want to call this one the producer equation, because it involves data of the producer. If you know something about the Earth rather than the board marker, what's causing it rather than what's experiencing it, then we're going to use this equation. That's my producer equation. By the way, the units for G, little g, little g, the units would be newtons per kilogram, or could be, anyone else? Anyone with the other one here? You know this. You so know this. The units for little g. Nope. If it's newtons per kilogram, it's not kilograms per meter. Newtons per kilogram or oh, come on. You so know this. Nope. Although it does hurt me that you don't know this. Meters per second squared. How did Sean figure that one out? Sean?
Because the newton is a kilogram per meter per second squared.
Okay. I thought you figured out an easier way, but that works. A newton is a kilogram times meters per second squared, so if you sub that in, the units cancel, and we have meters per second squared. Hey, the way that I knew it is because little g is 9.81, isn't it? We call that up until now the acceleration due to gravity. But really, like, how do you say the acceleration of gravity is 9.81 right there? There's nothing accelerating. A better way to say it is the gravitational field strength is 9.81. So from here on out, that's what we'll call little g, is gravitational field strength as opposed to the acceleration of gravity. And on the surface of the Earth, it's about 9.81. But now we have the ability to figure out exactly what it is wherever we are, not just assume it's 9.81 everywhere. Okay, does that make sense? Surface of the Earth, maybe it's 9.81. Top of Mount Everest, maybe it's 978 or something like that. Now we have the ability to figure that out. Okay, next equation. Little g is equal to F over m. Little g is the gravitational field strength. F is the force of gravity experienced. Experienced by a mass. And that's measured in newtons. M is the mass of the experiencer. So in other words, if you know something about what causes the field, that would be the Earth in the example that we keep coming back to, then you would use the blue equation. If you know something about what experiences the field, which would be the board marker in the example that we keep coming back to, then we would use the second equation. If you know something about both the Earth and the board marker, which one should you use? Either one. They should give you the same answer, right? What's the field strength caused by the Earth right here? Roughly, what is it? 9.81. What's the field strength experienced by the board marker right here? 9.81. So if I knew something about the Earth, I could calculate 9.81 using the producer equation. If I knew something about the board marker, I could calculate 9.81 using the second equation. The second equation that I'm going to call the, anyone? The experiencer equation. What units would you use for G? For little g again? Newtons per kilogram or meters per second squared. Same units, right? Same thing. 9.81 newton meters per second squared, 9.81 newtons per kilogram. Either one works. Whether you get it from the producer equation or the experiencer equation. Listen, guys, we have some masses up here, some equatorial radius. That means the radius from the center of something to the center of something. So we say the equatorial radius of the sun, that would be the radius of the sun as measured from the center to the equator of the sun. The Earth's moon, the radius from the center of the moon to the equator of the moon. Does that make sense? Okay, and then, of course, the mass of all these different things as well. Good news. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 of these different things. 10 masses, 10 equatorial radiuses. Okay, we're going to give you a quiz on this tomorrow, but I'm not going to make you memorize all 20 of them. I'm only going to make you recite 3 of them tomorrow. All right? You just have to give me 3 of them. No, I'll tell you which 3, but I'm not going to tell you what they are right now. I'll just tell you tomorrow what they are. You're not having a quiz on that. That would be the most ridiculous quiz ever, wouldn't it? Now, if you ever need these numbers, and you will need these numbers, they'll be given to you, okay? You don't need to memorize these. There's a couple of them on your formula sheet, yeah. Most of them are not, but if it's not on your data sheet and you need it, you'll be given that number, right? Okay, let's take a look at an example on page 218. Here's the question that says, calculate the magnitude of the gravitational acceleration of an object at the equator of the surface of the Earth and the Moon. What's another name for gravitational acceleration? Gravitational field, yeah. Gravitational acceleration, gravitational field. So we want to find in question A here, little g. What do we know about the Earth, the Moon? Well, we know the mass of the Earth. The mass of the Earth given to me on this table here on the previous page, the mass of the Earth is 5.97 times 10 to the 24 kilograms. We know the radius of the Earth, the equatorial radius of the Earth, on that sheet as well. It's 6.38 times 10 to the 6 meters. All those numbers that you need will be given to you in a question. You don't need to worry about that. Let's find the gravitational field, or the acceleration due to gravity caused by the Earth. G is equal to, wait a second here. Forget about the moon right now. Just the question involving the Earth. Is the Earth causing gravity or experiencing gravity? Causing. So which equation are we going to use? The first one, the producer equation, right? Little g is equal to big G times m over r squared. We know what g is from Cavendish. We know what m is from our table. Divided by r squared, 6.38 times 10 to the 6. We'll pull out the calculator and do this as a group. Watch me do this again. Hey, some of you still have trouble with punching numbers into your calculator. Watch me do this. We're going to say 6.38 times 10 to the 6. I'm going to press equals. I'm going to square that. There's the number on the bottom. Do the number on the bottom first. Then do the numbers on the top. 6.67 times 10 to the negative 11 times 5.97 times 10 to the 24. divided by the number that's on the bottom gives me 9.78. What units? Could be meters per second squared. What's the new set of units that we sometimes use? Newtons per kilogram. I'm going to use newtons per kilogram just because that's a little bit different than what we're used to using. Yep?
Significant digits, would you use the numbers on the dash?
Yeah, use the numbers on the table, yeah. So if you look back to this, we say all of these are 3 significant digits, right? So final answer should be rounded to 3 significant digits. It doesn't matter, that's a good question, William, but it doesn't matter where we get our data from, whether it's in the question or whether it's on a table or a data sheet. The number of digits that's expressed in is the number of digits that we use in our final answer. Okay, let's find the field strength on the moon. The mass of the moon is 7.35 times 10 to the 22. The radius of the moon, the equatorial radius of the moon is 1.76 times 10 to the 6. We're going to do exactly the same thing here, right? Finding the field strength on the moon. Would you expect that to be bigger or smaller? Probably smaller, right? G is equal to big G over r squared. The moon is a producer as well, right? The moon is causing gravity here, not feeling it. So we'll use the producer equation. 6.67 times 10 to the minus 11 times the mass of the moon divided by 1.76 times 10 to the 6. And we square that. Let's get the number on the bottom first, because that's what we do. Makes it a little bit easier to do the calculation. Let's square that. Let's say 6.67 times 10 to the minus 11 times 7.35 times 10 to the 22 divided by what we just got. It gives me 1.58. Well, that's quite a bit lower, isn't it? All right, next question says, compare them or find the ratio. We would find the ratio of these two. Ratio means divide. 9.78, the field strength caused by the Earth, divided by the field strength caused by the moon. We do that math, and we end up getting, what do we end up getting here? 9.78 divided by 1.58 gives us 6.18. You could just say 6.18, that'd be fine. I'd give you credit for that. Or you could, some people like to express a ratio like this, 6.18 to 1. Just like my age, the ratio of my age to your age is 2 or 2 to 1. The ratio of the Earth's field to the moon's field is 6.18 to 1. Go to the moon, you weigh 6 times lighter than you weigh on the Earth. You can jump 6 times higher. If you can do a high jump and clear 2 meters, well, on the moon you could clear 12 meters. All right. Let's take a look at these questions, please, on page 218. Notice we get the table copied for you on that page so you don't have to keep going back and forth. See what you can do in those questions now for the next few minutes.